All right. Welcome to this week's IIBA presentation sponsored by the Tampa IIBA. We've talked about how to do business analysis from a procedural or engagement standpoint. Then we talked about the differences between the engagement and the solution. And now we're going to start talking about the solution. Um, who am I? I'm some guy who's done simulation for way too long. And that involves computers, it involves programming, it involves figuring out what's going on, documenting everything, translating into requirements, design, implementation, test, and then application. So I've done this in a lot of different ways in a lot of different environments for a long time. So I think I have a decent viewpoint on how to talk about all the things that BAs do from a slightly different viewpoint. The more the merrier, the more ways you have to talk about the same things, the better chance you'll have of getting it to click in more people's minds. So I've talked about an entire list of kind of phases you go through in a project, and I won't belabor the whole thing this time. This time we'll really just talk about four of them. And this talk, mostly we're talking about the conceptual model. So that is figuring out what's going on and then figuring out how to document it and represent it so everybody, customers, investigators, analysts, programmers, database people, graphic artists, stakeholders, managers, and everybody else have a clear, accurate, shared, very thorough picture of what's going on. I like to think in very visual terms, so I've spent a lot of time over the years making pictures and diagrams of all this. So, my theory is there isn't one specific way to do this, even though visual representations standards like BPMN actually exist. So mostly, like I said, we're gonna talk about the conceptual model. Um, these four phases can be described as figure out what's going on. That's the conceptual model. Figure out what you need. That's the requirements. Figure out how you're going to do it. That's the design. And then make it happen. That's the implementation. Another way to say that is in the parentheticals. The conceptual model is the as is state, it's what's going on now. The requirements is the to be state in an abstract form. The design is the detailed version of the to be state, and the implementation is the concrete future state. So I have two blog posts. These are linked. They're on my website. Let me know if you have trouble finding any of this stuff. Two discussions about what I mean. So in the first link, I talk about working through from the conceptual model to the implementation as a process of working from an abstract state to a concrete state. And then the second link, I actually tell a story about my physics teacher in college from first semester of sophomore year. And he used to talk about how students, when they would get lost, they take out their calculator and try to just make something happen. And in reality, that's just a mess. Until you've got the equation that you're trying to solve set up, you've done the assumptions and simplifications, figured out what you're going to include and not include, there's no point in taking out the calculator. In theory, the problem is solved when you get the equation properly set up and formatted, and you know what you're going to do. And then only at the end do you plug the numbers in. So figuring out which equation to use is kind of the conceptual model and requirements. Getting it formatted properly and figure out what to include and not include is the design, and then plugging the numbers in and grinding out the answer is the implementation. So identifying the assumptions, capabilities, and limitations, that was one of the phases I talked about that isn't shown here. Defines the actual scope of what you're gonna do. So you might find out a bunch of stuff that's going on, but you won't necessarily include all of it or address all of it. You'll do only what's needed to develop the solution the customer needs. And if you do all the beginning stages right, the implementation should be a piece of cake. Practically builds itself. So, discovery is finding out what is happening. Again, it's a qualitative process. It identifies nouns and verbs. And then data collection is characterizing all those nouns and verbs with adjectives. That tends to be a more quantitative process. So discovery comes first, so you know what data you need to collect to support it and flesh everything out. Imagine you're gonna simulate or automate a process. What information would you need to do that? That drives what you need to learn. Again, if you're starting with a greenfield process and not an existing process, you basically flip the first two items. So before, where you had the conceptual model and then the requirements, you start with the requirements and then do the conceptual model and then the design and implementation. Or you can think of the conceptual model as part of the design. So in that case, it's figure out what you need, figure out what needs to be going on, figure out how you're gonna do it, then do it. All right, when it comes to process mapping, again, represent this visually in any way that works. I'm going to go through a few examples, give you a few things to think about, but most of all, you have some kind of bounded process that has a beginning, middle, and end, and you describe what comes in, where it goes, how it's changed, and what is produced. You describe the movement and storage of everything, not just stuff and not just information. BAs work for a lot of different kinds of businesses. If you think of Amazon, you've got lots of physical stuff. You have many different kinds of interfaces. You have personnel, you have transportation, you have connections with other companies, you've got databases, you've got uh, financial stuff, money moving around, payments, dispute resolutions, and so on. All those can be modeled, all those can be shown in diagrams. For whatever you're working on at any given time, the level of detail you depict should reflect that. Any process element within a map can be as deep and complex by itself. You can drill down as far as you want, but you should only go as far as required by the problem. For example, if you're doing a timing study, you don't necessarily need to know all the details of what's happening in one operational or process block. You just need to know how much time it takes. So state timing and other data can be included. Entities can be split and combined. I'll talk about, more about that in a second. Processes and entities may be continuous or discrete. I will say that comes from more of my experience as an engineer doing, among other things, heat and fluid flows, as BAs working with business and computer systems. Your work is overwhelmingly going to be discrete. It's going to deal with specific items that come and go. Some things that are moving within the system or some processes within it will never leave the system. So it's not always about stuff coming in and going out. It's about stuff changing and being used and doing different things. Again, anything can be included. You can have architectural elements that can be computers, networks, hookups, routers, anything. All right. So, looking at any one element, you can see a lot of stuff coming in from sources and a lot of potential outputs going out to customers. That's the SciPot model, working from the source to the customer. You can also turn this around and work backwards from what the customer needs, what outputs you have to provide, what process you need to create or modify to generate those outputs, what inputs are needed, and where you're going to get them from. Again, you can imagine this being anything. It can be a user getting information out of a computer system and writing it down or entering it into another computer system. If you automate that, all that is robotic process automation. There are different specific tools for that, but that kind of thing has been going on for at least 30 years, and probably longer. If you think fluid flows, just to give a different example, a lot of stuff can go into a tank, it'll all mix, and then stuff might come out as liquid from the bottom, and steam or other vapors or gases from the top. If you think of an assembly line building product, things go along and they hit a process and things are added to it, bolted on, screwed down, paint is applied. If you think of a machining operation on a piece of metal, different pieces might be carved off. There can be routing, planing, milling, drilling, all kinds of things. So if we look at an everyday example of a gas station with a convenience store, there's a car wash there, there are your gas pumps, your entry to the various underground tanks. There's an ATM, there are restrooms in there, there are lights, there are speakers, there's an air machine out there by the curb, there's a dumpster, there's a lot happening in that picture. Personnel, um, products, fluids, money going in and out. There are many procedures that have to happen. You're interfacing with many different suppliers. So the more you can identify what's going on in here, the better understanding you'll have and the better opportunity you'll have not to miss stuff. If we take a closer look, down here we've got a squawk box where customers can talk to people behind the counter and ask for help or tell them something's going wrong. You've got a fire extinguisher, you've got a cleaning wand and a vat of cleaning fluid, you've got some paper towels, you've got a speaker up here that might be doing announcements or playing music. And my favorite thing of all at gas stations is the trash can. I love those things. So if you look at a gas pump in detail, there's actually a ton of stuff going on. And how much detail you want to include, right, depends on what you're actually doing. So you might only think about the gas part of it if if that's what you're researching, but there are tons of other things going on. You can get as deep as you want. Here's a different way to look at these same things. So dispensables could include um, gasoline receipts in ink, right? Those things, same things are consumables also, um, but also including electricity and information. There's a network connection. There are a bunch of procedures for servicing this. There are maintenance issues. There are ways you have to use all the different parts of that. If you notice, look in the line or the hose for the regular gasoline versus that from diesel. There's a whole extension cord there. This is much longer. So this hose can go up to trucks and vehicles on flatbeds and boats and whatever. So you notice there's a stain here where stuff leaks onto the ground and that may require cleaning. There are a bunch of advertisements set out, and those probably rotate over time. So there's as much going on there as you want to think about. Another way to drill down into a process is to look at all the things that uh, an individual or machine can do. So this is a breakdown of one class of employee in a disability insurance underwriting operation. These were all the different kind of documents they could deal with. These are all the different operations they could do. And these were the amount of time it took for that kind of employee to do this operation on this kind of document. So the columns and rows that were populated were different for every different kind of employee, and there might be 30 or 40 employees in each process block all doing the same thing. Um, we did this particular project in two phases. One was a timing and capacity study. When we did the proof of concept and competitive approach for different business process reengineering approaches, we ended up winning and then did a more detailed design and implementation of a document imaging system that went into more detail than this and also automated away a lot of these operations. So that's where the money savings came from. Um, as far as procedures go, you can also talk about the how an entity goes through a process and what can happen. Um, these will sometimes be random or stochastic. So all trucks coming into a land border crossing go to commercial primary. Of those, about half go straight to the exit. About 10% go to an agricultural inspection. Some percentage go to a commercial x-ray. Of those, a small percentage go to a um, dock where everything has to be taken off the truck and inspected. And of those, a small percentage get impounded. So there are many, many ways to represent all this. And you can consider how the state of the element, entity, or customer changes on the way through a process. Um, I saw a nice presentation a few years ago on service design. And one of the things the lady talked about was a customer journey map. So you could think of a customer at Starbucks as going on one of these. So again, it's a way to look at things from every angle. So if we look at different kind of drawings, that is from a paper mill in Quebec City that I worked on. I think I did this drawing. So it shows the process equipment, it shows information about it, it shows information about what is flowing through. Here's a key. Um, so it shows the controls. Again, you can put anything on these drawings as long as you have a shared understanding and there might be industry standards. Here is a system I worked on for a nuclear power plant. I won't go into much detail. I spent 2.5 years living with this model and this system, and this is only page one of three. And I had probably 8 other models I worked on too. I got a career's worth of education about how to do all this stuff by working on it. Here is a land border crossing um, layout of a simulation we built in a tool we made to build simulations. It shows how different kind of vehicles and pedestrians go through um, different processes, and the characteristics and timing of all those processes could be set independently. That's an architecture study I did to figure out the minimum number of components that are reusable, um, that I should create to build a general purpose discrete event simulation tool, which ended up looking like that. So data collection, again, this is what you're trying to find out. I won't go into that in detail. These are many of the ways you can get that information. You can have people show you, you can look in documents and drawings and manuals. You can pick up data um, electronically. You can talk to people. You can take video. There are a bunch of ways you could do this. We talked about domain knowledge acquisition a little while ago. This is what you need to know to capture all the details of a process, analyze the operations, perform calculations, and make sure you don't miss anything. And in reality, the biggest way to make sure you don't miss anything is to document what you do, review it with the customer, and they will help you figure out if you missed anything. And I'll tell you from experience, that's not foolproof. So don't be bashful about really grinding on that point in discovery. So besides this being a really cool book, I've always loved this cover photo because it shows that how different things can look if you look at them from different angles. So all I'm talking about here is a way of analyzing what's going on to consider things from every possible point of view. UML is a particular way to do that. There's a nice book here, and there are many of them. Um, I'm not usually big on super formal methods. Um, Having all the certifications I do, I've learned that they're usually just um, one person's vision of doing the stuff you should be doing anyway. So ultimately, you're just trying to figure out what they're telling you and put it in your own words. So, in the end, the way you figure out whether you did something right is whether you look at the work at the end and you and the customer agree that you've captured everything and have generated what they need. Simulations are great for showing completeness if you do an animation because a picture is worth 1,000 words, right? But a simulation is, or an animation is worth 1,000 pictures because that's exactly what it is. So if we wanted to talk about UML in detail, it includes all these elements, but I particularly like to talk about in my own language. So you want to identify and then analyze every possible element, which are entities and which are process blocks and communications and interfaces. If you do that, you'll come up with a complete understanding. So you have to figure out every characteristic and then defines your variables, what type of variables you need, and what operations and what code you have to write. Anything that drives a decision or that's what you need. So you talk about what moves and doesn't move, what processes or is processed. You could think of a car pulling up to a gas pump. The gas pump does not move. The car gets processed and then leaves. That's one way of thinking about it. State change element can be in sequences and state changes, timing, duration, scheduling, storage elements where things can pile up or queue up. There are different kinds of storage elements. There are LIFO queues, FIFO queues, random in-out queues, which are often called bags, double-ended queues, and so on. You can also talk about how elements could be grouped. A while ago, I mentioned how there were 40 different employees in one process block in one process. Here's three in another. They're all doing the same thing. They're fed by their individual cues and they have one shared cue for any overflow. So those items will all have the same rules. They may have different open close schedules. There might be many things going on. So if you've ever done the exercise, brainstorming exercise, where you write everything you can think of down on post-its and put them on a wall someplace, and then group them according to things they have in common. That's kind of what you're doing here. So last slide. One of the main things we do as BAs is try to figure out how to do stuff better. So we can either make small incremental improvements where we just tighten things up and do them a little better here or there, or we figure out some total rearrangement or automation or um, application of new technology, which blows the whole thing up. So, Six Sigma is about removing variation. So, what you're actually doing is tightening up a process to make things closer to the target. Um, or what I've done mostly in my career is rearrangement and compression. So Six Sigma is doing what you're doing now better with less loss, and lean is doing more with less. There's a big difference between them. Those are some of the ways you do lean. And a lot of times when if you have a larger process, you will find one part of it, improve that, and then see how the whole system changes. And typically, the process you're going to be working on is whatever the bottleneck is in the larger process. And then you'll figure out what happens and then reattack the next constraint. All right, that's all we've got for this week. Thank you again, the Tampa IIBA. Cliff, what do you have?
No, we're good. Thanks, Bob.
Okay, everyone, have a great week.